Hi everybody, welcome. Without any further delay, I want to jump straight to the outline. There are lots of things to discuss. So first, I'll speak a little bit about me, why I'm here and what I do. And then we're gonna discuss why we need ADL in practice. And we're gonna move on with the name taxonomy, which essentially is a theory behind ADL. And of course, templates, no surprise here, templates interact with argument-dependent lookup, and therefore, sometimes they're either surprising cases or unspecified cases, as we shall soon see. And of course, finally, we're going to talk about customization points and customization point objects. I encourage questions throughout the talk. Please raise your hand. I'll get back to you as soon as possible. And in the event that I need some time to think about it, then we can always take it offline after the talk as a discussion. So a little bit about me. I was born in Greece. I did my bachelor's degree in informatics, and then I moved in Edinburgh to do my master's degree. And for the past year, I've been working for a company called Codeplay, and I'm a software engineer there. I'm part of the team that implements SQL. For those of you who don't know, SQL is a kernel group open standard, which essentially is a programming model that enables heterogeneous system programming in single source C++. Now, feel free to reach me out. I'm a very easygoing person. I would love to meet all of you after the talk. And here is my email in case you need me anything. Now, why ADL and why this talk? So in my opinion, ADL is fundamental to the language because it interacts with many of the core features. It interacts with namespaces, it interacts with templates, it even interacts with what it's fed to the overload resolution. And you will learn how actually ADL works. And also, with that in mind, we were gonna make non-intuitive cases simple enough. They will no longer be a black box for you. And of course, we're gonna discuss the common pitfalls and the traps, and we will see how we can guard against them by providing good guidelines. And generic code, customization points and customization point objects. We will see how ADL rocks in practice. And the references that I've used, templates, the complete guide, in my opinion, is a best book when it comes to templates. It's very close to the standard itself, but it's in a human readable form. And speaking of the devil, the C++ standard itself, which when it comes to really understanding a specific feature of the language, this is the best place to look up. And of course, a couple of papers that were written by the community and real life code that I've developed. I've made the mistakes, I fell into the traps, and I've learned a lot. And libraries that I interacted with, range STS, for example, where they introduced customization point objects, a feature that essentially does ADL on the user's behalf. And nlogman.json, which uses ADL for their serializer. I would like to give many thanks to Arthur O'Dwyer for his blog post and for a discussion that I had with him for ADL, and Christopher DiBella and Matt Godbold for giving me continuous feedback about my presentation. And when and why ADL? So you all know operator overloading, right? And what essentially looks like in your source code as an operator, the compiler takes that and transforms it into a function call. And it's very easy to see that from the following example. So in line number 3 here, we explicitly call the operator just as if it were a function. Whereas in line 4, we use a syntactic sugar form. Simple enough. But I'm here to tell you that if we didn't have ADL, line number 4 would be ill-formed. All right? We wouldn't be able to use the syntactic sugar form. So you're gonna ask, do we need ADL? Yes, we saw the first reason, right? If we didn't have ADL, we would brutally defeat the purpose of operator overloading. But it's not only that. It's actually that C++ has non-member functions, right? And sometimes these functions are a part of the interface of a specific type, even though they are non-members. And for that, we need to treat them uniformly. Turns out ADL is the answer to that. And templates. Templates undergo a process called two-phase lookup. And ADL is fundamental. Without it, the usability of templates would be greatly reduced. On the contrary, if we have unconstrained templates, they can be a source of very weird errors, right? Some people refer to them as ADL bytes. Now, name taxonomy and name lookup in a nutshell. Name taxonomy is important because it allows the programmer to reason about their code. Essentially, when the compiler sees a name, and what I mean by name, let's say a function name, it must look it up somehow. And the process of looking up that name depends on the name taxonomy of the entity that we refer to. And fortunately, the standard defines name taxonomy in a non-intuitive way. And we can't rely. Yes, please. You will see later on. Just hold on for a second. So yeah, the standard mandates name taxonomy in a non-intuitive way. And we as programmers, we can't rely on the standard for day-to-day programming. And hopefully we can get away by remembering the four things. We can say that a name is either qualified or unqualified. And if it's a template, we can say that, and if it's a template, it can be dependent or non-dependent. So how does the compiler process a function call? It turns out it's a two-step process. The first process is a name lookup, which essentially describes how we construct a set of potential candidates. And we take that set, and if it's greater than one, right? If there are more than one elements in that set, then we feed that to the overload resolution. And the overload resolution describes the process that this set is reduced down to one, the function that we end up calling in our source code. So also, the subject of overload resolution belongs to a different talk. We're not going to cover it here, but in case you're interested, please refer to the Templates, a Complete Guide, chapter 16. It has everything you need to know. So again, we say that a name is qualified, and in that case, it's looked up by the rules that are specified by qualified lookup. And we will also add some more rules if it's a template later on. And we can say also that if the name is unqualified, it undergoes the unqualified lookup rules. And again, if it's a template, there are some extra rules. We're going to see all of them in a second. So let's see how qualified names work in practice. The lookup scope is always implied by the qualified construct. And of course, a qualified name is when that name is prefixed with either the scope resolution operator or the member access operator. It's very easy to visualize this from the following example. You have a structure, you have a pipe structure, and you have a member connect. And in line 6, you have a qualified call, which essentially searches inside the scope. The implied scope is pipe, and it calls the right function. You already know that. You've used that. You now also know that it has a name, and it's called qualified lookup. And of course, p.z is ill-formed. There is no z inside pipe. It makes sense. Unqualified names. Unqualified names actually undergo a two-step process. And the first process is unqualified lookup, and sometimes they undergo an extra step, the argument-dependent lookup. And we can describe that with two sets, right? The first set will be the set produced by the unqualified lookup, which we will call U, and the second set is the set produced by the argument-dependent lookup, which we're gonna call A. And now we can say that if the set U contains a declaration of a class member or a block scope function declaration that is not a using declaration, and here an example, suppose you have a function f, and inside that function you have extern some function name, this rule essentially will block ADL. And the third case, which I want you to remember because it's gonna come in the very end, is that a declaration that is neither a function nor a function template. And customization point objects, as we will see later on, uses that rule. And then the set is if that's the case, then the set A is empty. Otherwise, all right, we take the union of the set A and the set U and we feed it to the overload resolution. Now, let's see how unqualified lookup works in detail. That's the first step, by the way. So, unqualified lookup searches subsequent scopes. You can imagine that as it propagates up, right? And again, our favorite example, although this time we make an unqualified call to connect. And we search inside Z, there is nothing inside Z. We search outside, and there is nothing in the global scope, so therefore we get a diagnostic. Again, it makes sense. But now if we call F, we search, there is nothing in here, we go here, and whoops, we found F, and we call that F. Now the second step, the argument-dependent lookup step. So we can imagine this, in order for me to explain how we build up the argument-dependent lookup set, we need to know two more sets, the set of the associate entities and the set of the associate namespaces. And we're gonna explain how we construct these sets, because we use these sets to build the argument-dependent lookup set. And I'm gonna explain this just if it was a game. And essentially, we need to classify each argument with a category. And that category depends on the type that we are passing. So what if the type that we're passing on a function call is a fundamental type, that is an int, a char, or a float? Then in that case, the set of the associate namespaces and the set of the associate entities is the empty set. So if you think you're clever and you try to do something like that, it won't work. So essentially, you have a namespace, you have your void func, you have an f which accepts an int, and then you make an unqualified call. You get a diagnostic. It doesn't work out. Now, what if T is a class type? Then the set of the associate entities is a class itself, and indirect or direct-based classes, and if it's a member of a class, then that class itself. And the set of the associate namespaces is the innermost enclosing namespace of its associate entities. And you can see that very clearly from the following example. We have two namespaces. We have a library namespace and a user namespace. And inside the library namespace, we have again pipe and connect accepts a pipe. And later on, in the namespace user, we derive from libpipe, user pipe derives from libpipe. And then connect now accepts a user pipe. When we make an unqualified call to that at line 13 over here, first unqualified lookup is triggered. And unqualified lookup finds nothing in the global scope, so the unqualified lookup set is empty. And we also proceed to the argument-dependent lookup, and we see the P. P is a class type, and therefore the set of the associate entities is lib : pipe and user : user pipe. And the set of the associate namespaces is lib and user. So in the end, the argument-dependent lookup set contains both lib : connect and user : connect. And of course, this is fed to the overloader solution, and the overloader solution picks up user : connect as a better candidate. Now, moving on. What if T is an enum? Then then E is a enum itself, of course, and if it's a class member, then the member class. And the set of the associate namespaces is an innermost namespace of its declaration. And again, I will present you an example here. We have a user, we have an enum class color, and we have a function f that accepts a color. Now, when we make an unqualified call here, unqualified lookup again, searches outside, finds nothing, so that set is empty. We proceed with the argument-dependent lookup step, and we feed user. So sorry, the argument-dependent lookup set will contain user : f, and that's the one we end up calling. So this call is perfectly legal. Now, what if T is a pointer to x or a pointer or an array of x? In that case, we completely forget about the pointer. We don't care, and we look at the underlying type. And obviously, the underlying type falls down to the previous categories that I've just described to you. So let's see an example here. Again, the same example, but this time connect accepts a pipe pointer. And when we make an unqualified call to connect and we pass a pointer to a lib pipe, then ADL is able to find lib : connect. Now, what if T is a function type? Then in that case, we need two things: the function parameter types, and obviously the return type. We can see that from the following example. Again, same thing, although this time process accepts a pointer to a function that takes a pipe object and returns a void. And we define such a function into the global namespace, and inside age we make an unqualified call to process, and we pass custom. Now here, there are two things. Unqualified lookup finds nothing, it is empty, and argument-dependent lookup proceeds. We see first the return type. The return type is void. What did we say for fundamental types? There is no set of associate namespaces, and there is no set of associate entities. So we now look at the parameter types, And we already covered this, right? It's the second rule. So we know by what I've discussed previously that the argument-dependent lookup, the A set will contain lib colon process, and therefore this is valid code. Now, what if T is a pointer to a member to a member function of a class X? This is very simple enough. All you need to remember is the fifth rule and the second rule, essentially the previous rule that I've just described, and the second rule, which is a class. Now, as you can see here from the following example, you have we make an unqualified call. Sorry, let me rephrase that. We have a library namespace again. We have our structure pipe, and we have a function z that this time accepts a pointer to a member of pipe. And we do that. We construct such a pointer to a member, and we call z unqualified. And this works again because of the rules I've just described to you. You already know this by now. And what if t is a pointer to a data member of a class X? Then in that case, we need to take then the set of the associate namespaces and the set of the associate entities is the class itself, which is the second rule, and also we need to take into account the type of the member. And we can visualize that from here, from the following example. Oh, what? Yeah, that shouldn't happen. Sorry for that. Moving on, templates and ADL. Sorry. So before we get into templates and ADL, I would like to discuss some terminology with you. So is it a function template or a template function? We need to be precise. You will see why. Is it a function template or a template function? I'm gonna quote here Walter E. Brown. It's like saying milk chocolate or chocolate milk. The one is a beverage, the other one is a candy for children. They are not the same thing. The right terminology is function template and class template. And what about specialization and what about instantiation? So instantiation is a process where we substitute each of the template parameters with the template arguments. And if that process succeeds, we end up with a specialization. But a specialization is not necessarily produced by the process of instantiation. We can always explicitly fully specialize our template. Now moving on, we need to revise a little bit now the rules, and I'm going to revise the second rule. And the second rule is what if T is a class template specialization? Then in that case, it's the set of the associate namespaces and the set of the associate entities contains what we've said before, plus we now take into account the types of the template arguments and the template arguments. And you can visualize that from the following example. So we have a library namespace and we have a class template called pipe. And again, we have user, and this time user brings up defines water type, and we have an unconstrained template. An unconstrained template that takes a parameter pack of universal references or forwarding references. And we make an unqualified call and we pass to match anything the specialization produced by instantiating pipe with water pipe. And so what happens here? So first, unqualified lookup. Unqualified lookup finds nothing, so that set is empty, and we proceed with the argument-dependent lookup. And now argument-dependent lookup builds first the set of the associate entities. And the set of the associate entities is lib : pipe and user water pipe. So the set of the associate namespaces is lib and user. And for that, we finally feed to the argument-dependent lookup set user : match anything. And therefore, this call is valid. And I must say this now, this is very dangerous code. And you will see why later on. Now, what is a dependent name and what is a non-dependent name? So, a dependent name is when we say that a name is dependent if it depends somehow in a template parameter. And I have a question for you. Which of the following declarations are type dependent? So line number 3, I want you to raise your hand if you believe that line number 3 is actually a dependent name. Good. And what about the second one, line number 9? Is this a dependent name? Raise your hand. Good, you're smart. Exactly, it's not. Exactly, because we know the type, right? We have the type there. So this is simple code. What about two-phase lookup? Now, non-dependent names, unqualified or qualified, are looked up by the rules I've described to you. But if the name is an unqualified dependent name, there is an extra step. At the point of the instantiation of the template, we undergo an argument-dependent lookup, and this can be explained by the following example. So we have the namespace lib, and we have a class template called pipe, and we have a function template called process, and we make an unqualified call to connect, and this is a dependent name. So while this template is being parsed, right? Unqualified lookup finds nothing for connect, but it's not complete. It waits until the template is instantiated. So the compiler proceeds. We define water pipe, and we define also connect. And inside aids, we make an unqualified call to process, and we pass an object, a specialization of by instantiating the template pipe by water pipe. And here, in that case, we trigger ADL. And we have a second example here where we explicitly put the template arguments as a need. So, is the first case valid? From what I've described you so far, is the first case valid? Is this valid code? Raise your hand. Exactly. What about this? Is this valid code? Can anybody tell me why this is not a valid code? No? Could be that case later on, but that's not what happens. Yeah.
It needs to see a declaration of process as a function template.
Exactly. C++ is a context-sensitive language, right? So when we are here, the compiler, first this is a valid code, right? And here, when the compiler is trying to look up and decides, is this a function call? Or is this a statement of the form process less than int greater than the parentheses? Now, this is an egg chicken problem, right? And it cannot be resolved. So if you want to make it work, all you need to do is add a declaration. But in C++20, there is a paper which actually changes the grammar rules. So this is valid code in C++20. And yes, you're going to get an error, but later on, and you're going to get the correct error. That's the important thing. Now, friends and ADL. I would like to talk a little bit about history here. So I was born in 1994, and back then it used to be the case that in-class definitions of friend functions were essentially injected to the outer scope. They were polluting essentially the unqualified lookup. And that was very problematic, turns out, and later on it was replaced by argument-dependent lookup. I'm not gonna go into details of how that thing works exactly, but I'm gonna say to you that if you wanna Google it, you can search Barton and Knapman trick. And now, let's see how friends work with ADL. We have a library. We have a namespace library, and we have a class template called pipe, and we have a friend function called connect. And here, pipe is the injected class name, right? It's actually pipe of T. And then later on, in side 8, in line 12, we create such an object, and we call connect unqualified. So here, again, unqualified lookup will find nothing, but also argument-dependent lookup will find that friend. And it's important, you can use that as an optimization, because essentially with that, you're saying, hey, that friend function, I want it to be available only by argument-dependent lookup and not by unqualified lookup. It turns out that this can be very dangerous because if your friend is available by unqualified lookup, and if your class supports, if you can construct your object of that class with an implicit conversion, you might find yourself shooting yourself in the feet. Now, the 2.5-step dance, right? So you probably have seen this code. Many of you, who of you has seen this code? Can I? Exactly. Anybody? Okay. So moving on. So we have a namespace user, and we have class template pipe, and we have a function process again, and we do that. We do that because we want to be as general as possible, right? I can explain you exactly why. So first, if T is a type defined in the standard library, then if that's the case, then ADL, from the rules that we've just described, will be able to read that out. But what if T is a type that is defined in some other namespace, and it cannot be reached by the generic, it cannot find the generic template? That actually helps us do that. And also, not only that, it adds an extra layer. That extra layer says that if that type T has a user-defined overload of swap, because potentially the user knows better, can optimize how to swap for their own type, then in that case it's gonna pick that overload. So not only we are general, this will work for any case, right? Even if the user hasn't provided an overload. And now we can see that, okay, this is an error. This should be the same type because TT. Yeah, let's be precise. And now we call p.process and we pass A and B. And this works, all right? If inside that type there is an overload of swap, it's gonna be preferred. And if it's not, it's gonna fall back to the generic swap. It's gonna fall back to the stud swap. And now, beaten by ADL, unconstrained templates, and unspecified behavior. What will the following code call? Any insights here? So essentially what we do is we define a structure, we have a user, we have a type alias for the specialization produced by instantiating the set pointer with a user type, and we have type, which accepts a my type, and we have oops, and make an unqualified call in line 12. Any insights? What's gonna happen here? What do you think it's gonna call? Anybody? Almost. Is that the case? Always? So, what does this call?
Can you repeat his answer so that we can hear?
Oh, sorry?
What was the response? What did he say? I can't hear you.
Oh, yeah. They said that it will call to tie, which is almost correct. Almost correct.
Undefined, or at least unspecified, because we have no idea whether stood tie was provided by memory.
Exactly. And this is very dangerous code.
Can you repeat his response?
Repeat. Yeah. Sorry. They said that this. They said that this is unspecified behavior because we don't know. The standard doesn't mandate what memory includes, right? And also, I have another question. Now let's see how that works. We call and we make an unqualified call to tie here, and as we said, std tie finds that, and the overload resolution resolves to tie to be a better match. Now on Clang and GCC, this finds to tie. On MSVC, it finds user : tie. So this code is non-portable. Has any of you fallen into this trap before? There you are. Very, very dangerous code, right? Let's move on. Beaten by ADL. 2. Iterators and algorithms. Anything that behaves like an iterator is an iterator. Do you agree? Can anybody see any problem here? No? Okay, let's see. So we have main, and inside main we have a row array, a stud array, and a vector. And we call unqualified find. So I have a question here. Is this valid code? Raise your hand. Who believes that this is actually valid code? You have a question, or are you raising your head? This is a valid code. Okay. Our friend there says it's a valid code. What about this? Is this a valid code? Raise your hands. Right? And what about this? The third one. Maybe. I like that. Who said maybe? Raise your hand. There you are, Arthur. Oh, many of you. Nice, nice. You know that. I like that. So the first example here, A is an int star, right? And what did we say about fundamental types? Int star has no associate namespaces and not associate entities, and therefore this cannot be called. Now what about this? This again returns an int pointer, so this is an invalid code. But this is the most this is the most important part. This is actually again this code is not portable, and the reason that this code is not portable is because that we don't know if the implementation does something like type def iterator in star. It could be a type, it could be not, and if it somehow resolves to be an in star, then too bad for you. Your code will not be portable. So here, please, when you're using standard algorithms, always qualify your calls, all right? Always qualify your calls with stud. And now some guidelines. Now, always remember the interface principle, right? It comes from Herb Sutter, and Andrei Alexandrescu. So keep the types and its non-member functions that are supposed to be together in the same namespace. And if they are not meant to be used together, then in that case, put them in a different namespace. The second here comes from me. Always qualifies calls to the STD algorithms, right? I find it to be the best practice, and I never had any problem in practice. And these two are coming from the C++ core guidelines. And avoid highly visible unconstrained templates with common names. And this is actually the case. There was a bug in LLVM, thank you Arthur for that, of stud apply. And they had to rename it to select because it messed up with stud apply. And define overload operators in the namespaces of their operands. That's actually the interface principle. And also I'm gonna add here, prefer to make them a friend, right? And define them in class. That way you don't pollute the unqualified lookup and you have an extra safety net under your belt. And now let's talk about when generic code doesn't quite cut it. So you know that generic code is not always optimized for user-defined types. And I can give you an example for that, right? Swap. Swap is generic enough, but sometimes maybe the user knows better. And as a library, you wanna do two things, all right? The first thing is that you wanna cover the general cases intuitively, but also allow the user to customize the behavior when that is required. And you can imagine that, right? Suppose we have the library. Suppose we make a call to stud swap ranges. Stud swap ranges calls swap unqualified, and the reason it does so is that Well, if you haven't defined your overload, then it's gonna fall back to the generic case, the stud swap. But if you define your overload, it's gonna prefer that over the generic implementation. So essentially, the library, from a library's point of view, you get both of the best worlds. You get and the general case and the customized case. And also, begin is also a customization point. Is a customization point. It's called unqualified for the range for loop, right? It calls begin and end unqualified. Now let's see how they actually work. So here we overload swap. We have my type. We overload it for our own type, and we fill it with random input. It's supposed to have an int here. That's and we call swap ranges with begin and begin. And essentially this will call the user overload. But there are downfalls to that. There are downfalls. Can anybody point them out? Why is this? It's good code, but what is the problem with this code? Any of you? There are two things here. No. Sorry?
Just curious. I guess it was legal earlier. I was kind of curious. Do we not compete with std begin, the context of the global function, and the std begin of vector?
No.
There's no issue there in terms of ambiguity.
Oh, sorry. Yeah. Can you repeat your question?
No, you need to repeat it so we can hear it.
Yeah, I couldn't because. Yeah. I'm sorry.
Global namespace begin function versus member begin of vector.
Yes.
Is there ambiguity there?
No, there is no ambiguity. But
Because the using brings in.
no.
Okay.
No.
Does the no accept?
No. Now, two things. The first, please, Chris.
Is it because we have to put using declarations above our call to swap ranges?
No. Yeah. Is it because we want to put using declarations? Sorry.
Is it because we need to put using declarations with std begin instead of end before we actually make unqualified calls to begin and end in our call to swap ranges?
No. So the. Yes.
This feels like it could be right. Is it because your struct is defined with snake case and your vector is defined with?
No, that's not it. So there are two things here. Okay, there are two things here. First, the first one is that we can't pass swap as a first class object, right? If we have some generic algorithm, we can't really pass swap, right? It's not gonna work very well. And the second thing, all right. The second thing is that that's pre C++ 17. Swap was unconstrained, right? So if the user overloaded swap in a way that it would pass the constraints of the main of stud swap, it would be called. And imagine that, right? I can give you an example. Imagine begin. Begin must return an iterator or something that behaves like an iterator. What if you make it return a void? It's not gonna be checked. Pre C++ 17. And the solution to that, it's actually customization point objects. And customization point objects essentially do ADL on the user's behalf. And they are objects. And the best part is that you can also pass them around and they're gonna do the right thing for you, no matter what. And this is the approach that is followed by the ranges library. And I'm gonna present you here a simplified version of it. But if you want, you can take that and you can build upon that, and you're gonna reach to the actual ranges v3 implementation. Now, customization. Sorry. Moving on. Suppose we have here we have a namespace library, and we have the namespace detail. And inside here we have the poison pill, which I'm gonna explain to you shortly what exactly it does. And sorry for that. here is the poison pill, and then if there is any user-defined I'm sorry, let me repeat myself. So we have a function template try to swap, and it accepts an int. And this thing over here, it's FINE friendly, right? Essentially, it tries to call swap unqualified. And if it finds an overload, that's actually valid code. If it doesn't find an overload, then this will be removed by FINE, and it's gonna fall back to the try and swap, to this version. And also, the poison pill protect us from pulling stud swap, right? If somehow the type that we pass has the standard as the associate namespace, this will make this ambiguous, and therefore we're gonna fall back to the no ADL tag. So no matter what, no matter any circumstance, stud swap will not be considered. And here we define a type trait, and essentially this type trait tries to call swap with a value 42. And of course, if that thing is valid, it's gonna call it, and if not, it's gonna fall back to this case. And what's the return type? It's no ADL tag, and we're using is same v, and if it's equal to the no ADL tag, then it means that there is no ADL, there's no overload. But if it is, then there is an overload, and that type trait is true. Now here we have a structure, and it's called swapfn, and inside that we templatize the call operator. And we templatize it in a way that if it's ADL swappable, then we will return the call, an unqualified call to swap. And we know that already it's gonna call the user overload. And now here, we fall back, and we enable this in the case, that there is no user-defined overload. And we can fall back to some implementation that we have in some detailed namespace. And I must note here that the poison pill is, I think that the poison pill is not really needed, and the reason is that stud swap is now constrained. So there isn't any case where it will read out stud swap. Now, we do this, and essentially this actually makes an object, and now swap is an object. Swap is no longer a function, it's an object. So we can pass it around. And if we can pass, in quotes, stud swap around, and it does, it does ADL for us, we have a first-class function that we can use in our algorithms. And this is very powerful. Now, let me give you an example of that, right? The user namespace, by the way, this has an address, right? It's an object, it exists. And here, inside, we have a class template pipe, and we instantiate pipe with a vector of int. And later on, we swap, we overload swap for our user-defined type. And here, in our function, in our function f, we create two objects of this type, and we call lib : swap p1, p2. And this is beautiful because essentially it goes back here, because this is a template, right? Now the type deduction kicks in and says, oh, is there a user-defined overload? Yes, there is. Instantiate this, and it resolves to the right call. What if we had using lib swap here? Would it be any different? Would we have any different behavior? Can you raise your hands? Exactly. We get the same behavior, all right? So no matter what we do, we always end up having ADL, having the customization point object doing ADL for us. And as I said previously, we can also call any algorithm, and we can pass the swap. by the way, this would be lib colon swap, right? And in that case, inside that algorithm, it would resolve to the user overload. So we get both of the best words. And the best part is that the constraints are not bypassed. And we can do the same design for begin. And it's even more powerful because we can add more spin overloads. We can check if there is a member, right? If there is a member, prefer the member. We are essentially controlling both ADL and the overload resolution. This design is very powerful. And that's me. Thank you for listening. Do you have any questions?
Hi. Thank you for the talk. That was good. Could you go back to 61? I think your list of guidelines.
Which one, sorry?
61. I think your list of guidelines. I think it was out. No, I think it's after that.
6.1.
Oh, yeah, sorry.
Oh, you said 6.1. Yeah. No, here?
There, that's it. Speaking as a library maintainer, Herb and Andre are speaking truth if you can promise that the namespaces and types will never ever change.
If the namespaces and the types?
If the namespaces for your functions and the namespaces for your types will never ever change.
Okay.
That is not really very well guaranteed. Speaking as the chair for Library Evolution, I'm deeply hoping that we're going to change a whole lot of stuff out of std ranges into std over like the next 10 years. Unless your library maintainer actually promises for all time these two things come together, don't rely on ADL. Their guidance is good for short-term programming, bad for long-term programming. That'd be my suggestion.
Thank you very much for your comment. I really appreciate it.
I guess to have a discussion in the comments here, it strikes me that that's sort of a special case of if you put things in the same namespace, you may be implying that they are part of the same non-member interface, right? The fact that, for example, std swap is in the same namespace as std vector implies maybe a relationship there, but then we also have things like std, name of function, std find is in the same namespace with std vector, and that's more of an accidental historical artifact. And there is no distinction between the two, and wouldn't it be nice if there were, but the only tool we have for that, I think, is make lots of little namespaces, and I don't think anyone wants to do that either, so it's a mess.
Thank you.
Could you elaborate on how introducing new scopes can test? I'm guessing that just introduces ambiguity rather than if you... There was one spot where you introduced using std begin the function, and other times where you can entirely bring in another namespace.
Why would we not bring the whole namespace?
Oh, no. Could you just elaborate on? There are times where I might need to use operator stream insertion or an inheriting constructor or something to the effect of
because using directives are not included in the set of the argument-dependent lookup. So you need to do a declaration. You need to say, hey, using std begin or using std end.
Sure, but I'm under the impression that you still need them for scope resolution. Because doesn't scope resolution short circuit? For example, if I have a parent class that has a function that I choose not to overload, and
can you give me an example?
Probably not one that I could express in words too quickly, even though I was just about to try. Perhaps the question might be better served for after then. I was just searching for using statements, though. They seem to be finicky.
Yeah, that's...
I want to know if I say using std operator stream insertion, for example. So I'm not talking about using namespace. I'm talking about a particular actual instance. Does that bring in everything from that namespace?
No, it brings only the declaration. And actually, it's a declaration. It brings it as a declaration into your local scope. That's what it does.
Okay.
Does that answer your question?
To the best of your understanding, I suppose. I probably have to think about it a bit more. Thank you, though.
Okay, thank you. Yes?
If I could rephrase my understanding of part of that question, one might ask, why do I have to say using std swap and using std begin, but I don't have to say using something operator, plus, or using operator left shift? Aren't those also found by ADL?
You're pretty close to what I'm answering.
Yeah. And the reason that you have to say using std swap is because you want to not only use ADL, but also fall back to std swap, even for things like pointers. So by saying using, you're saying a fallback path that you want to use when ADL fails. Using is actually bringing things into the unqualified set.
Like the overload paradigm, where you using all base classes version of the same signature entity.
I believe that is what using does.
Maybe I'm poorly phrasing the question. I was just curious if there was an elaboration.
Anybody else? Thank you.